Okay, or the first part of recursion. So recursion is one of those things that you hear about, and people kind of think of it as like a very like a very mystical, very powerful concept, and it definitely is very powerful. But it also kind of follows some like very fundamental logical ideals, right? Um, so let's see, who wants to volunteer just to explain the code on the left? Okay, Joe. Do you want to? Okay, do you want to just like walk us through like what happens to the code on the left if I actually invoke a countdown?
Yeah. Okay, so if we invoke countdown, can I use a number as an
Yeah,
example? With 5, let's say. Mm-hmm. I'm just going to ignore the console log right now, but the first time we invoke it, n is 5. So we're going to check if the first if statement is true. So we're going to ask, is 5 bigger than 0? The answer is yes. So we're going to invoke countdown again with 4 this time. We check the first if statement again. 4 is still bigger than 0, so we do it again with 3. Then we do it again. 3 is bigger than 0. Countdown with 2. We check if again. 2 is bigger than 0. Do it again with 1. 1 is still bigger than 0. Then we do it again with 0. And it fails the first test, so it goes to the else statement and the console log's done. So it does a countdown from 5 to done.
Yep. Okay. So I'll kind of explain like the verbal logic behind it, and then I'll just diagram it out, probably in a nauseatingly explicit fashion on that whiteboard, and it's going to get very like confusing very quickly. But so recursion. The most important thing about a recursive function, and by far the most important thing about a recursive function, much like a while loop, is you have to set a condition in which this will stop eventually. Recursion is powerful because it can do things, up to an infinite number of times, but it's also dangerous because if you don't give it in any scenario, it will literally just keep going until it eats up all your computer's memory, or the computer has some safeguards in place that says, hey, I think this is a mistake, you probably meant to stop it at some point. Okay? So when you create a recursion function or try to use recursion, always know when to stop. All right? Looking at this code on the left, we don't need to do too much about what it's doing right now, but reading it, it's pretty clear to me where it stops, right? If this, we use recursion because we're calling ourselves over and over again, right? But the stopping point is when this else. So basically, when n is larger than 0, we want to keep going. But as soon as n is not larger than 0, then we stop. Okay? So right away, like that should tell us at a very high level, okay, this is the endpoint. This is almost like where we're trying to get to, right? We want to get to a point in which n is less than 0, or n is not greater than 0, because then we can actually stop running this function. For now, like think of recursion as a way to do something that, for the most part, you probably are able to mimic with a while loop or with a for loop. But there's a few kind of scenarios in which recursion just works a lot better for what you want to do. But in this case, on the far right, we have a function that takes in a number, and then we just go through a number, right? If the number is 10, we go through from 10 all the way down to 0, and we console log out the number, and then we say done iterate, right? On the left-hand side is the code that Pedro just walked us through. It does the same exact thing, except now rather than just doing it with a for loop, we actually do it recursively. And I know this doesn't explain what recursion is or how it looks in practice, but just know that you can mimic a lot of the effects of recursion with iteration. Yeah.
So how often would we use recursion? How often would we use it?
You use recursion when you feel like you need to use recursion,
No, but
and you use iteration when you don't feel like you need to.
No, but is it often? Not often? How much?
I mean, it depends on what you're doing, right? Like, if you're doing recursion is best used for when you're trying to do things that you're not sure how many times it will take.
Okay.
So, for example, if I want to simulate the roll of a die, and I want to stop when I get a 6, could we do it with a while loop? Yeah. But in that case, recursion actually would probably be a better fit, right? In this case, even counting down the liftoff of a rocket, can we do it with iteration? Yeah. But recursion in some ways works a little bit better because it removes a lot of like the manualness of us having to set explicit boundaries on it.
Okay.
Even though we still need to set boundaries on it, otherwise it won't ever stop. So yeah, that wasn't a great explanation, but like
No, but
as with anything like this, it's like are you going to use it? You're probably going to come across it. I don't know if you use it every day. If you work at a highly algorithmic trading shop, maybe. If you're trying to do front-end web development, maybe not as much, right? It's a tool, like anything else. Like how often do you use trigonometry? Well, if you teach trigonometry, probably a lot. Otherwise, I don't really see much of a need. Anywho, so how does recursion work? So I'm trying to think if I should skip this slide almost and just start diagramming out for how it works, which I'll probably end up doing that. So and these slides are definitely all available. So when I skip over them, it's not like say they're not important. I'm just saying in the order that I want to talk to you about it. Like let's just table this for now, and then when you review these slides, you can actually go back and kind of get a sense of kind of where they fit in the overall framework. But the second bullet here, right, is when I use recursion, how do I know when to stop? And implicit in that question is, well, how does the computer track what's running at any given moment, right? And that's where we're introduced this concept called a call stack. And a call stack is actually something that's incredibly powerful that you definitely need to know, especially if you want to get a job as a developer, because in a lot of job interviews, they ask a lot about call stacks, right? Because call stacks are like kind of like the very, very fundamental data types or data structures, I should say, of how a computer executes code and how really you should be thinking about code. Okay, so the best example for call stack is imagine you're at a buffet line and you have a stack of plates, right? So let's just say let's say here's like a buffet line, right? And then I have a plate here. Let's say I'm the dishwasher, right? I come and I put a plate here, right? This might fall apart very quickly, but anyway, I put a plate here, right? So and this is like a clean plate, right? So the next person that comes to grab some food from the buffet, what do? They take the plate off, right? And so the analogy there is, let's just say I'm running a function that's like console logs out hello, right? What the computer does is says, oh, okay, you want to run a function that console logs out hello. Great. Let me add it to my queue of things to do, right? And then once I finish console logging out hello, I'm done, right? So this no longer needs to be here. So I can actually take this off the stack of my plate. Okay. What if I need to run 2 console logs in a row? How does that work?
Put another play. Oh, in a row.
Close the drop when what happens when I console log out 2 things in a row. Use the Sharpie, it's really cool. No one wants to draw that Mallory, there you go. So I'm on console log out 1 and then on console log out 2. Draw for me the process. Like draw it while talking about the process.
Here's plate 1.
Okay.
Plate 2.
Okay.
And then console log 1. This
Okay.
one will drop down. Console log 2.
Okay.
Right?
Yeah. I think for the benefit of the class, because I think you were saying right in front of it when you were
Sorry,
drawing it.
yeah.
I think what she do was I have my first console log here, right? I added to my stack of things to do. Then I have my second console log on top of it. I do my first one, so the first plate goes away then. The second plate drops down to where the first plate was, and I do my second plate. Okay? So if that was the scenario, then just to kind of keep that in mind, right? If I have 2 lines of code, the first one says console log out number 1. The second one says console log the number 2. In what order will those things console log out at? Based on the description that you just gave. 1 and 2. Okay. Okay. So the interesting there was the way the computers actually handled that, right? Is because the computers see that, and this is the word that was on the last slide, right? Is this idea of synchronous. Synchronous means I do it in a certain order. There is a very clear order in which I do things, right? And computers, for the most part, are actually incredibly adept at doing one thing at once, or one thing at a time. When we want to talk about like multi-threading, it's a different conversation altogether. But for the most part, for now, think of computers as only being able to do one thing they're not good at parallel processing, if you will. Okay. So the way the computer would see those two console log statements is like, okay, so you have two console log statements, right? One above the other. Well, clearly you're going to run the first one first, then the second one second, right? Otherwise you wouldn't have written it in that order for me. So on my first plate, I'm gonna add a plate here that's gonna I'll say console log out 1. And then I'm just gonna do it. Because I know that you want to run the next console log after you run the first console log. So I'm actually going to run console log 1, take it off my queue. This is dying. Take it off my queue, and then afterwards, I'll actually. Okay, well, that's a purple one there. Oh yeah, I'll take the purple one too, just in case this blue one doesn't give out. So I console log out the first one first. Oh. Okay, and then I console log out. Then I say, okay, great, I've done with the first piece of code. Okay, you have another code. Therefore, let me add another plate now, a console log 2, and let me execute that. And then when I'm done executing that, I'm pretty much done, right? So the interesting thing there is, in that scenario we just described, there is never ever 2 plates, so to speak, or never 2 jobs in the queue. Because the computer sees you want me to do 2 different things, but you want me to do them A and then B. So guess what? I'm just doing 1 at a time. I'm gonna do A, stop, and then I'm gonna do B, and I'm gonna stop. Okay? So that's kind of how a computer sees synchronous code when we run it. The reason why recursion now is a little bit different, or why the recursion is gonna change all that, is also due to the fact of how computers see jobs, okay? So if I have a recursive function call, right? So try to figure this. When I say console log out 1 and then console log 2, console log 1, that command only finishes once it does everything kind of in that command, right? Once it prints out 1, then it stops. When does a function end?
When you hit return.
When else?
When you hit a curly brace.
I'm sorry?
When you hit a end curly brace.
Yeah, exactly. So those are 2 sort of right. Like a function only ends once I hit like quote unquote, let's say the end of the code, the end of the block, right? If you hit a return somewhere in the middle, yes, it also ends the function. But for now, let's just say that a function ends when you do all the things that you were supposed to do, right? So if I now go back to the countdown example that we were looking at earlier. Okay, so let's go to this countdown example now. Did I mistype something? Oh, it's not a. Why is this not? Oh, because I never called it. Cool. Okay. So let's look at how this will look in context of that. Okay. So at some point I'm calling countdown and I pass in 5, right? It's pretty easy. Okay. So the computer says, all right, great, David. You only want me to do one thing here. Count down 5. Let me do it. So this first plate here is going to be pretty simple, right? It's just count down. I'll say C D to make it shorter. But this is going to be count down 5, okay? And I say, all right, great. I have one job in my stack. Let me go do it, okay? I go back to line 1 now. Like first thing, console log out N. Let's say this is my console log screen up here, right? Like, okay, great, 5. This is going really well. Next one, is N larger than 0? Yes, it is. So I want to go inside this loop now, right? And then now, here's where interesting is, okay? So this is 5 minus 1, right, which is 4. And at this point, what this function is telling me to do is like, hey, let's run countdown 4, right? And now at this point, here's where we see the stack actually start building up again, right? Because I can't erase the stack because I haven't finished this function yet, right? Even though in this case, it might look like we've finished it, so to oh, actually, you know what? This would actually be really cool. Let me add another console log down here really quick. And I'll say done with iteration number, and I'll make this N, okay? See how, great, okay. So Anywho, so anyway, n is still 5, right? We're here, we get to here, and we're like, okay, let's run it. I can't erase this plate yet because I haven't ran line 8, right? So my function isn't done yet. But I'm also telling you, hey, by the way, before you do that, do you mind running this other function? And so here, I'm actually starting to say, well, okay, you have this thing on the queue, but let me put up another plate on top of this queue now, right? And this is going to be CD of what? 4, okay? Another really important thing to know about computers, this is called what, like LIFO, L-I-F-O, last in, first out. It means a computer will always, by default, try to do the job that's currently at the top of the queue, right? The reason why I was using the buffet and the plate example is, if you have a stack of 10 plates, right, and you want to go and grab, like earlier we were getting pizza, right, like you grab the plate more or less off the top, right? You grab the latest plate that was put on there. You don't go to the very bottom of the stack trying to get the very first plate, right? You get the very top. And that's how computers do this too. A computer will now look at this call stack and says, well, I have 2 things to do, but call 4 is currently at the top of my stack. I should be doing countdown 4 first. The 4 I then finish up countdown 5. Okay? So then we've actually started another iteration of countdown now, right? Except what is n now? It's 4, right? So now we go through it, and the next line says console log of n. Okay, great. My goal is to finish up countdown of 4, so I can get to countdown of 5, finish up countdown 5, right? I need to do 4 if I do 5. Let's finish up 4. Well, at this point, is 4 greater than 0? Yes. And so then now I'm back on line 4 now, and it says, okay, before you finish countdown 4, do you mind running countdown 3 next? I'm like, okay, fine. Let me do this now. I need to add another stack on my plate, right? Because I haven't finished countdown 5, I haven't finished countdown 4, but I'm also telling the computer, hey, do countdown 3 before you need to finish those. So now you see my plate starting to build up, right? And without kind of belaboring the point here, if I do countdown of 3, this is going to print out 3, and it's going to tell me to do what next? It's going to tell me to do, hey, before you finish 3, which you need to finish 4 and 5, do you mind doing countdown 2 first? And so I'm actually just going to go down this path, really for a while until I get to countdown 1. Okay? So now n is equal to 1, I have to print out 1, and then I do, is 1 greater than 0?
Yes.
Yes. Okay. Okay. So now I'm doing countdown what? So now I'm doing countdown 0. Notice how my queue or my stack here is 6 jobs deep, right? I never finish countdown 5. I never finish countdown 4, 3, 2, or 1, because before I can finish each function, I've been telling the computer, say, hey, do this other thing instead. Hey, do this other thing instead. So now we're at countdown, and n is equal to 0, okay? So once again, we go to line 2, console log out 0 for me. I can do that pretty easily. Great. Is 0 larger than 0? No. Okay. So now I can do an else, and I can do console log done. Well, that's really nice. I don't need to write this down. You can see on the right hand side, right? Like, that's just what we have so far, right? 5 through 0. And then finally, when I do countdown 0, I've finished up with this countdown, so I can actually write done, okay? And then, after I log done, what do I do? What line do I go to next?
8.
And I go to line 8, right? Because now I'm just going through the code in linear order, right? I'm done with line 6, go to line 8. It says done with iteration. I'm passing in n, which is, in this case, 0. So that's why this prints out now. Now, am I done with countdown 0?
After you do that.
Yes, right? I console log this out. I didn't hit a return yet, but I hit the end curly brace. Right here, right? So in any case, I know that this function is done. And now, finally, I can actually go back and say, great, I finished that up. I can remove this countdown 0 off my plate because I ran this function. I ran this function to the very completion. Okay, everyone good so far? And now the problem is, okay, great, we finished countdown 0, but we still haven't finished countdown 1 yet, right? So the computer looks and says, okay, I have 5 more things to run. The top of my plate is finishing up countdown 1, right? So where did we leave off on countdown 1? What was the last thing we ran when we ran countdown 1?
Line 4.
Right, we ran line 4 to run countdown 0, right? So we just finished line 4. We finished countdown 0, right? So now what line do we run next?
8.
Well, no, 1.
So if I'm running it through, I just finished line 4. What line do I go next?
Oh, sorry.
Shatavia? Where?
I don't know.
Okay. Well, what if this was just console log David, right? Let's replace this with console log David. If I was to go here, I console log David out. What line do I run next?
Then you go 8.
I mean, I go line 8 next, right?
Yeah.
Because I finished. I took a detour to do countdown 0. I finished countdown 0. This was in an if-else loop, right? I already did the if, so I'm not going to look at the else anymore because I know it doesn't apply to me anymore. And so I pick up where that finished off. And the last thing I finished off was saying, done with iteration number. Well, what's n in this case? It's 1. So I log out done with iteration number 1. And what does that mean for my stack now? I can take off countdown 1, right? Because I've reached the end curly brace of that particular instance. Okay? And so now if I'm a computer, I'm like, okay, great, we're making progress. What's next? What's next is countdown 2, right? Because countdown 2 is the highest up on my stack right now. Where do we leave off on countdown 2? So what line is next? 8 again, right? And so I logged out, done with iteration number 2, and lo and behold, I've now finished with countdown 2, right? So I can take this off my call stack as well. And I mean, I think hopefully you're seeing the pattern here now, right? We finished 3 and 4 in the same exact way, right? We're basically we're basically going to this code, stopping at line 4, doing all this extra work, and we finish and we're saying, okay, great, now I can keep going with where I was before, right? So I basically log out. I'm done with iteration number 3, and I can wipe out countdown 3. Same thing with 4, and now I'm back to countdown 5. Okay, and at countdown 5, I finished up countdown 4. I now go back to countdown 5, and then I can log it out. And at that point, I'm actually done with this entire function, right? Because I finished countdown 5. I have no more other code to run. And yeah, as a computer, I'm like, this is my happy steady state. Yes, what?
So I know that you said it's not exactly the same as a for loop, but like when you're looking at a call stack for a for loop because you don't run a new function, is it just one stack? Or is that not helpful?
No, I mean that. So yeah, so basically your question is if we do this in a for loop, how would it look,
Yeah.
right? So in a for loop, well, let's just write it really quick so we can have a reference to it, right? So I'm going to comment this out, and here I'll say, function countdown. I've taken number of n, and then just doing for var I equals 0, I is less than n, I plus plus, I is less than or equal to n. I'm sorry?
Oh yeah, it's going down.
You're starting at n.
Oh, you're right. Yep. Let me fix that 1 second. And then console.logout done. Done. And then this is greater than or equal to 0. And then I equals n. Okay, great. Oh, did I miss? Oh. Okay. Yeah. Oh. Cool. Okay. So if I was a computer and I was running this, right? I say, okay, you're starting to run countdown 5, right? So let me start running it. CD of 5. Okay, you have a for loop. Okay, great. In the for loop, well, we're not creating a function scope, right? I'm just going through this. So I say, let me log 5. Okay, I'll log 5. Then I'll log 4, 3, 2, 1, 0. I'll log out the done for you. And then my function's done, right? at no point am I ever spawning any new subtasks because everything there goes in complete order, right? Like if we think about the for loop as 5 loops, of when I equals 5, I equals 4, I equals 0, right? Like I equals because we're starting off with I equals 5, the loop for I equals 5 finishes completely before we ever move on to I equals 4, right? And so that's why we're not building up like a backlog of jobs here, right? Because we go to I equals 5, we finish it, like you can even write like oh, we do I equals 5, and then we finish it out, right?
Yeah.
And then we do I equals 4. It's like having like 5 console logs in a row, right? Exactly, right? It's like having a console log, having 4 console logs in a row, right? Like we'll do them, we'll do in an order, and we always finish the previous loop before we go to the next one, right? So that's why there's no backlog here. Whereas, what? Go ahead.
Sorry, just if you have callback functions,
Yeah.
like in the middle of the function,
Yeah.
does that create a new stack?
Yeah, call functions does too, right?
Okay.
And in some ways, the only thing about callbacks, like if you invoke a function within another function, you're basically creating that, right? So countdown, there's no callback, we're not passing the function, but it's invoking a function, right? So it creates like another thing, right? Basically, if you do anything that keeps your current iteration of code from finishing up completely, to take a detour and do this instead, that's going to create a new job on your stack, right? So, I mean, there's no, well, it could be bad because if your computer's not large enough, it will break, right? And there's actually a lot of really, like, it doesn't take that much to necessarily break a computer because essentially when you do recursion, you're kind of moving into this land of like exponential, like the number grow exponentially, not linearly. And so it wouldn't be very hard for something to break like without a very high number, without a really big number. But if you need to do it, you can do it, right? That's no, I mean, recursion I think is probably more memory intensive because like when someone talks about how large your computer's memory is or your RAM is, your RAM is random access memory, so that's what you currently have going on at any given time. That basically is a good proxy for how many of these plates you can handle at once. So the higher the RAM means the more memories you can kind of handle at once, if you will, right? So if your computer has very low RAM, then it means you probably can't do too many of these plates at once. And so if that's a limitation, then you probably want to be very careful around how you use recursion. In that case, a for loop might work a lot better, right? Because if you have low RAM, it can handle one plate at a time. It just takes a bit of time, but it's like whatever, it doesn't matter, right? Recursion, it takes up more, like I guess like short-term memory, if you will. So okay, so that's kind of the version of iteration. But does this make somewhat sense to folks, right? Basically, when I run countdown on line 4 here, I'm running another brand new instance of countdown, right? With its own value and its own console logs and everything else. And I can't finish that until I finish all the code within it. And that code in the middle is telling me to take a detour. I have to finish that first before I consider myself to be done, right? It's almost like you're building like a house, right? Like let's say if the goal is to like take your family on vacation, right? You need to go pick up your parents, and then you need to go to the airport. Then you need to get on a plane. Like these things have to happen before you move on to the next thing, right? You can't just say, oh yeah, let me go to the airport first, and I'll pick up my parents afterwards. Like, well, probably not a good vacation for your parents. But the idea is that you can't jump in between these. You have to finish this thing before you move on to the next thing. So yeah, so going back then here to this so just so I know I skipped over this initial slide, right? But this is all this first bullet point is trying to do is trying to say that like whenever you call a function within another function, it like interrupts this original function, right? Because now the computer says, all right, before I finish up your function, I need to go do this other function thing instead. So let me go do that, and then when I finish that up, I'll come back, pick up where I left off here. Right?
Yeah.
Cool. All right. So that's that slide. That wasn't it. Okay. So yeah. So the call stack, right? So a function call is always added to the top of the stack, and it becomes the most important thing to the computer. Whatever's at the top of the stack is always the most important thing to the computer. And when it finishes, the way that I erased it, in computer terms, you call it a pop off, right? Like now we do array.pop. You take the last element and you remove it. Same thing here, right? You have a stack. You take the last element, latest element, and you remove it. So same conversational syntax, but okay. Sorry, I'm just okay. Cool. All right, so let's do this really quick. Okay, so who wants to draw the stack for this function? Alex, wanna do it?
Sure.
Great. Yep. So they actually wrote out the function names for you, so you can just like write those out. And I'll tell you that in the first whatever. Actually, before I start doing it, let me just copy and paste this code to our REPL, so we have like the line numbers to use as reference. Probably make it a little bit easier. Okay. Cool. Okay. Cool. So this is a code, and we're starting on line 19. Okay. So let's do it.
Okay. So for 19, meet me. So var first we're at meet me function, and then it goes to say hello. So we pop up to say hello. And then function console log.
So you have a marker in your hand for a reason.
But we're not. I haven't been asked. There hasn't been anything to draw yet, right?
Well, so at line 19, I'm running meet me.
Okay.
So at the very least, to the computer, now I have this job called meet
Okay.
me.
So meet.
That's fine, yeah.
Okay. So meet me, and then it tells us to go to say hello. So. I should have made that bigger. It's very small. And then it says console log hello. That,
Yeah. So pretend this is your console log over here on this side.
Okay,
This is your console log screen here.
cool. So hello. And then say hello is finished, right? So we can erase it.
Do you want a napkin?
Yeah.
Here.
You were so hesitant. You
Okay, so now that's done. And so we move on to the next thing in the meet me function. So say how are you? What? So then we go to say how are you, and then we start that, and that tells us to go to wait for response. Cool. And so let's go there, and then that tells us to console log waiting. Right?
Console log.
Yeah. On the right.
You have your screen on
On the
your
right.
console log.
No, I'm being consistent where it tells us to do it, and then I'll do it, and then I'll erase it. I'm being.
But it's part of
Console log
wait
doesn't
for
add to the stack.
response. Is it part? It's part of the wait for response function. So you already have a stack.
Okay. Oh, okay. Yeah, I think. Yeah, that makes sense.
Oh yeah.
And then that's done. So then we erase it. Okay, I see. Yeah. And we're still in say how are you? At a console log. How are you? And then that's finished. And then we're done.
Cool.
And so
Yay. Good job. Yeah, and if we run it, that's exactly how we're gonna see, right? Hello, waiting, how are you? Cool. So yeah, that is the call stack in action, right? We build meet me, say hello. Ta-da, and we're done. That was it. Okay, cool. So recap here. Once again, super important. Recursion. Always have a base case. Always have a scenario that you are very, 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 very confident will finish. Okay. The only when I say very confident is like the roll of dice, right? Like theoretically, it's possible that it doesn't finish for like 600,000 rolls, right? So like there's always kind of like these edge cases, but for the most part, like define your base cases accordingly in a way that like you're pretty sure that it will reach that point, and then you stop. The third bullet here, the base case is not defined in terms of the function itself. What that means is like the base case really should be coming from outside of the function, because if it's coming from inside the function, then every time you rerun countdown, for example, you're going to generate a new version of the base case. And so you really want the base case to be something that's passed through from iteration to iteration, so that you can reach a point in which at some stage you'll say, okay, I can actually stop now. Okay, and then second one, define the recursive case, which is the function call itself. That's in our case, it was when n is greater than 0, and then the recursive case is defined in terms of itself. I think that's it's kind of a weird phrasing. I think that just means that like the recursive case is based on the thing you're passing back and forth, right? So in our case, it was n-1, right? So as I did that, like the input that you give it is a direct way to determine whether or not I'll run it again and again and again and again. Basically, all of this is to say that, look, if I was to read through your function, is it very clear to me what variable is being passed through from run to run? Is this variable being changed in a way that I can see a scenario in which I will actually stop running this someday or at some point? That's it, right? So with our countdown function, the number n was our like thing that was being passed from run to run, and at every single run, we were taking 1 away from it, and we stopped it when n is basically 0. And so there's a very obvious world in which that's going to be reached. So we say, okay, this looks like a valid recursive function, right? It's a little bit of an art as well as a science, because like when you're looking at the code, for us, countdown is really easy. But at some point, you might say like, oh, mathematically, is there a way that this finishes? So you might need to kind of do some math on your side to figure out if the recursion doesn't end. But you just want to make sure that you're pretty confident that it eventually will. And then here we're gonna have someone else do this for us. This is a factorial. Is everyone familiar with what a factorial means in math? Basically, the syntax here is if I do 5 factorial, 5 factorial is equal to 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1, and then you usually stop at 1, right? So the other way to write this is, n factorial is equal to n multiplied by n minus 1, n minus 1 multiplied by n minus 2, ... until you reach 1, right? So, don't worry about like the math part of this as much, because we actually write out what the factorial function is for you. But let's see. Kelly, do you want to draw this out for us? Yeah, do it. Okay, so let me put this in. I'm sorry? Okay, so that's a function there, and then the purple marker, and then yeah. So starting on line 10. There you go. Starting on line 10. I guess there's no console logs here, right? Anyway, starting on line 10, then just take it away.
Okay. So it's like
Well, so let's just call it like factorial 5. Right now.
Okay,
Right, so-
factorial 5.
Yep.
And then it goes back up to the top, so then it's
So which line of code are we at now?
So we're I just did the first. Wait. Yeah, I just did factorial 5. So then it goes. Yeah. Sorry, right.
I don't know where you're at right now.
Well, I just
So okay, so we do line 10, right? And then
Yeah.
what line do you go to next after line 10?
3
Line 3. Okay, and then
or
what?
4.
Sure, 4. Yeah. And then
So then I
yeah, right.
return, and then I go to 7 because n is not equal to 0,
Okay, so now you're on line 7.
Yeah.
Okay.
and that's what I just did. Right.
Um,
So like n times or in fact or 5 factorial.
let me keep going.
Is that right?
Well, so line 7 is 5 multiplied by factorial of what? Right. And so all I know is at line 7,
Right.
eventually we call factorial of 4.
Okay. Call factorial 4 with that.
Well, we calculated, right? We calculated.
Yeah. So 5 times 4 factorial,
Sure.
and then it returned. So then I don't know where it goes from there.
Okay. Alright, you mean.
Okay, great.
So I guess just kind of elaborate a little more depth, right? So we start off with like kind of like 5 like fact. I'll just call it F, okay? Let's say I call it F of 5. Okay, that's line 10, right? I go to line 4, doesn't apply to me. So lines 4, 5, and 6 don't apply to me. I'm now on line 7. Line 7 says, hey David, give me back to me n, which is 5. So good so far. Those are numbers. I know how those work. Multiplied by factorial of 4. Well, what's factorial of 4? I don't know yet, right? Like, yes, it's a function, right? But I don't know what it is yet. So in order for me to finish line 7, I need to actually figure out what factorial of 4 is, right? I do this, and I go back to 4, n is now 4, right? In this case, I look at this and think, okay, is this recursive? Yes. Does it make sense? Yes, right? Because in each instance, I'm decrementing my number by 1, and at some point, I stop on reaching 0, right? Because notice how the way that function is set up here is that if n equals 0, I return 1. I never run this, right? So I'm either returning on line 5 or I'm returning on line 7. And if I return on line 5, I never hit line 7, which is great because that's my base case, right? That's when my factorial, that's when my recursion is done. When I reach line 5, I know I'm done with my recursion, okay? So all I know from this, and I think, so Kelly did draw this for sure, which is that, okay, this is going to try to get to a world in which it's going to give me 5 multiplied by, I'll say f of 4, okay? So this basically means, all right, let's figure out what f of 4 is. Is n equal to 4? Or no, is 4 equal to 0? No, so I skip 4, 5, and 6. Ah, here we go. Factorial of 4 is equal to 4 multiplied by what? Factorial of 3. Well, what's factorial of 3? I have no idea, right? So now, but that tells me I just need to start up another stack here to say, all right, David, try to figure out what factorial of 3 is. I do this as 3 multiplied by factorial of 2. And so I just keep building this up higher and higher and higher, right? Factorial of 2 is equal to 2 multiplied by factorial of 1. Sorry, I think I multiply factorial of 1, which gives me now factorial of 1 is equal to 1 multiplied by factorial of 0. Okay? Exactly. So now I'm at factorial of 0, right? Does everyone see how I got to this part of that? Right? Like, I had to do all this work because all I need to do was figure out what factorial of 4 was. Well, I didn't know. So, eventually I need to do factorial of 3, factorial of 2, 1, 0, right? and now I'm at 0. If n equals 0, whatever, return. I return 1, right? So I know this is 1. And lo and behold, in every other instance, I need to do some more math, right? Call another function. Here I don't. I know it's just 1. So I can actually get rid of this now and replace this with what now?
1.
It's just 1. And once I figure this out, I'm done, right? It's just, now I'm just multiplying two numbers together, which computers are extremely good at, right? So now f of 1 is equal to 1 times 1, which is what?
1.
Great. So now I know f of 1 is just 1. So I can actually now get rid of f of 1 because I've solved that puzzle, if you will. And now I can replace this with 1. And now f of 2 also kind of solves f of 2, right? What is f of 2 now? F of 2 is just equal to 2. And so then now this is equal to 2. And without belaboring the point, f of 3 is going to give us 6. 6. And that means f of 4 is going to give us what? F of 4 is going to give us 24. And now at this point, I can actually finally finish up f of 5 because I know f of 4 is now, right? And now I'm just multiplying two numbers together. 5 times 24, which gives us 120. And so at the very last row here, I'm going to return back 120 as my answer, right? And so that's how, in this case, factorial was being used, is that we were actually just able to, like, it seemed like we were almost done, right? If we just knew what factorial 4 was, we would finish with this on the first run through, but we didn't. We actually need to keep doing factorials over and over and over again until we got to the very end. And so factorial 5, which equals 5 to factorial 4, which equals factorial 4 multiplied by factorial 3, etc., etc., etc. And now we finally reach our final happy case in which, oh look, no more factorials, no more other functions. I'm just giving you a number back. Great. I'm very good at using numbers with other numbers. So then I work my way backwards, and we get back to this answer where factorial 5 is equal to 120. Everyone clear on kind of how we drew that diagram and why it happened the way it did. Cool. Yeah, so recursion. Recursion is very powerful, and because of that, try using smaller numbers first if you can. Just because when you do a lot of big numbers, you eat up a lot of memory really, really quickly, and a lot of times the computer memory is going to run out before you even have a chance to kind of get to figure out where the root of the problem was. So usually you actually want to start, you know, as small as possible. It's always a good rule of thumb with recursion. And then if you're having trouble with writing recursively, think about how it will look iteratively and make sure that your recursive logic follows a very similar path. And then lastly is just that diagram that I just drew there. Like, if I come around and you're like, I'm stuck, I don't know why this is doing this, I will make you draw a diagram for me. So it probably helps if you already draw it before I get there. But yeah, like, I will make you, like, just how like when we do pass by reference, pass by value, I usually make you draw the arrows for me. Like, I'll make you draw that stack for me so we can at least be agreed upon in terms of like if we're understanding computers operate in the same way. Cool. All right, it's 3 o'clock. I will give you guys until 3:45 for this workshop, and I'll launch into recursion 2. And the goal here is to finish up with recursion lecture by 4:15. We'll take a 15-minute coffee break then, and then we'll do problems until 5. The recursion 2 problems until 5, and then the class ends at 6:30. So maybe 5:15. And then for the last hour, it'll just be open review on whatever you guys want to talk about, all right? Sound good? Cool. All right, let me Slack out groups to you all.